Have you ever stopped to think about what everything around us is really made of? I mean, down at the fundamental level.
Yeah, not just that there are atoms, but how their tiniest parts actually behave.
Exactly. And understanding the electronic structure of atoms is, well, it's the key to unlocking all of that.
It really is.
Today, we're doing a deep dive, drawing from a fantastic source, a whole chapter in that classic textbook, Chemistry, the Central Science.
A really solid foundation for this topic.
Our goal here is to unpack the core ideas, pull out some surprising insights maybe, and connect these sometimes tricky chemical concepts to the real world.
Basically giving you a shortcut to understanding this invisible world that, dictates how materials behave. We'll cover the principles, the history, the applications, make it all click together.
Okay, let's jump in. We start in the early 20th century, a revolutionary time for physics, right? Einstein, relativity.
Huge stuff. But for understanding atoms, the real bombshell was quantum theory. That's what we need to grapple with.
And it starts with light, surprisingly enough, electromagnetic radiation, or radiant energy, as it's called.
Absolutely. You can't understand electrons without first understanding light.
So we often think of light as a wave, like ripples on water.
That's the classical picture, yeah.
And these waves have properties. Wavelength, that's the distance between peaks,
Uh-huh.
and frequency, how many waves pass by each second.
And the key thing, the universal thing,
Right.
is their speed in a vacuum. All electromagnetic radiation, radio, visible light, X-rays, everything travels at the speed of light. Peace.
Mm-hmm.
About 300 million meters per second.
Wow, and wavelength and frequency, they're linked?
Inversely linked.
Oh,
Always. Longer wavelength means lower frequency, shorter wavelength means higher frequency. Multiply them together, you always get C.
that electromagnetic spectrum figure in the book, figure 6.4, it's just vast. Gamma rays, smaller than atomic nuclei, all the way up to radio waves longer than football fields.
It's an incredible range.
And visible light, the stuff we actually see, is such a tiny, tiny sliver of that. Just 400 to 750 nanometers, roughly.
Which is why different types have such different effects, right? Radio waves carry signals, infrared feels like heat, X-rays penetrate tissue. It all comes down to that wavelength and frequency.
The book mentions an example, sample exercise 6.2, with the sodium lamp's yellow light at 589 nanometers. You can actually calculate the frequency from that wavelength using the speed of light.
Exactly. Phi on a coin equals C. Basic but fundamental.
But, okay, this neat wave picture wasn't the whole story. There were problems.
Big problems. 3 key things it just couldn't explain.
Right. Black body radiation, the light hot things give off.
Yep. Then the photoelectric effect, light knocking electrons off metal.
And emission spectra, those weird specific lines of light from gases.
So 1900, Max Planck tackles black body radiation. He makes this daring assumption.
Which was?
That energy isn't smooth and continuous, it's quantized. It comes in little packets, little chunks. He called the smallest chunk a quantum.
So energy is like stairs, not a ramp.
Perfect analogy. You can be on step 1 or step 2, but nowhere in between. Energy comes in discrete amounts, and the amount E is linked to frequency by a new constant, H Planck's constant. E equals H times E. E equals high.
But why don't we, notice this in everyday life? Energy seems smooth.
Because Planck's constant H is incredibly, incredibly tiny. The individual energy steps are just too small for us to perceive on our scale. But down at the atomic level, they're hugely important.
Okay, so Planck starts it, then Einstein picks it up 5 years later.
1905. Einstein uses Planck's idea to explain that second puzzle, the photoelectric effect.
The electrons getting kicked off metal by light.
Right. Einstein proposed that light itself behaves like a stream of these energy packets. He called them photons. Each photon carries energy EE die.
Okay.
And to kick an electron off the metal, a photon needs enough energy to overcome what's called the work function, like an exit fee for the electron.
So it's the energy per photon, the frequency that matters, not how bright the light is.
Precisely. Intensity just means more photons. But if each one doesn't have enough energy, high enough frequency, nothing happens. If they do have enough energy, even one photon can knock an electron out. That insight won Einstein the Nobel Prize.
And this fundamental idea, photons, it leads to real tech, right? Like lasers.
Directly. Laser light amplification by stimulated emission of radiation, built first in 1960, based entirely on these quantum principles. Now they're everywhere. Barcode scanners, surgery, data transmission.
Amazing. And the flip side, high-frequency photons like X-rays. Their high energy is why they can be dangerous.
Exactly. They pack enough punch to damage biological tissues.
Yeah.
So this whole line of thinking forces us to accept that light has this weird dual wave particle nature. Sometimes it's a wave, sometimes it's particles.
Okay, so light is weird. How did this start changing how we saw the atom itself? Let's talk spectra.
Right. You shine white light through a prism, you get a continuous rainbow, all the colors blurring together.
But if you zap a gas, like neon in a sign or sodium in a streetlight,
You don't get a rainbow. You get a line spectrum. Just a few sharp, specific lines of color, like a barcode for that element.
hydrogen spectrum is apparently really simple. Just a few visible lines.
Remarkably simple. A violet, a couple of blues, a red. And scientists like Balmer and later Rydberg found mathematical formulas that predicted those wavelengths perfectly.
But why? Why only those specific lines?
That was the million-dollar question. And Niels Bohr in 1913 had an answer.
He took the existing model, Rutherford's mini-solar system atom.
Yeah, nucleus in the middle, electrons orbiting like planets.
But that model had a huge flaw, didn't it? Classical physics said those orbiting electrons should radiate energy away, spiral inwards, and the atom should collapse.
Which obviously atoms don't do. They're stable. So Bohr, inspired by Planck, said maybe the classical rules don't apply here. He proposed electron energy is also quantized.
Okay, how did his model work?
3 key ideas were postulates. 1. Electrons can only exist in specific orbits or states, each with a fixed energy. No in-between energies allowed.
Like the staircase again.
Exactly. 2. While in these allowed states, electrons don't radiate energy. That's why atoms are stable. And 3. An electron only absorbs or emits energy as a photon when it jumps between these allowed states. And the photon's energy, high, exactly matches the energy difference between the states.
So those spectral lines, they're the photons released when electrons jump down from a higher energy state to a lower one.
Precisely. Bohr even calculated the allowed energy levels for hydrogen using a formula with a number n, the principal quantum number. N1 is the lowest energy, the ground state. Higher n values are excited states.
So an electron absorbs energy to jump up, emits energy as light to jump down.
And the light emitted has specific frequencies, specific colors corresponding exactly to those energy gaps.
Yeah.
That's why we see discrete lines.
It explained hydrogen's spectrum perfectly, but it wasn't the final answer.
No, it had limitations. It really only worked well for hydrogen, one electron. It couldn't handle more complex atoms.
Right.
And it still didn't fully explain why electrons behave this way, or fundamentally why they didn't spiral in. It was more of a brilliant set of rules that worked, rather than a deep explanation.
That's still crucial, right? The idea of quantized energy levels, quantum numbers.
Absolutely foundational. It paved the way for the next big, really mind-bending idea.
Which was, if light can be a particle, maybe.
Maybe particles can be waves.
Exactly. Could an electron, a tiny piece of matter, behave like a wave?
Louis de Broglie asked that very question in 1924. His hypothesis, yes, matter has waves. He even proposed an equation. A particle's wavelength is Planck's constant divided by its momentum, mass times velocity. Concludes his part me.
But we don't see, like, baseballs acting like waves.
Because their mass m is huge, so the wavelength is unbelievably tiny, completely undetectable. But for an electron, its mass is minuscule.
So its wavelength is significant. Comparable to X-ray wavelengths, actually, like in sample exercise 6.5 in the text. And this wasn't just theory.
Nope. It was proven experimentally with electron diffraction. Beams of electrons fired at crystals created diffraction patterns, just like X-rays do. Direct evidence that electrons have wave properties.
And this wave nature is useful.
Incredibly, the electron microscope. It uses the wave nature of electrons. Because their wavelength is so much smaller than visible light, they can resolve much, much finer details. Magnification up to 3 million times.
Whoa. Okay, so electrons are waves and particles. Things are getting weirder.
And about to get weirder still. Werner Heisenberg, 1927. The uncertainty principle.
Ah, this one's famous. You can't know everything precisely.
Pretty much. You cannot simultaneously know both the exact position and the exact momentum or velocity of a subatomic particle like an electron. There's a fundamental limit. X times mv is greater than or equal to h4.
And it's not just that our measuring tools aren't good enough?
No, it's inherent in nature. The very act of measuring one property, say position, inevitably disturbs the other property, momentum, in an unpredictable way. It's fundamental fuzziness.
The book mentions this really bothered Einstein. God doesn't play dice.
It bothered a lot of people.
Hmm.
It forces you to abandon the idea of electrons having definite positions and trajectories like tiny planets.
Mm-hmm.
Instead, you have to talk about probabilities. Where is the electron likely to be?
Which sets the stage for quantum mechanics proper.
Exactly. Enter Erwin Schrödinger, 1926. His wave equation brought together the wave and particle nature of the electron. This is quantum mechanics, or wave mechanics.
So what comes out of solving Schrödinger's equation?
For hydrogen, you get solutions called wave functions, symbol PSI. Now, T itself doesn't have a direct physical meaning, which is a bit strange.
Okay, so what's the point?
The point is psi-squared. That tells you something physical. The probability density gives the probability of finding the electron at any given point in space around the nucleus.
Ah, so not an orbit, but a probability map, an electron cloud.
Precisely. We ditch Bohr's orbits and talk about orbitals,
Yeah.
regions in space where there's a high probability of finding the electron.
And these orbitals are described by quantum numbers again.
Yes, but they emerge naturally from Schrödinger's math this time, not just put in by assumption. Three main ones describe the orbital itself.
Okay, what are they?
First, the principal quantum number n. Same n as in Bohr's model. Positive integers, 1, 2, 3. It tells you about the orbital size and energy level. Bigger n means bigger orbital, higher energy.
Makes sense. Second.
The angular momentum quantum number, L. This can be any integer from 0 up to n minus 1. It determines the orbital shape.
Shape, like different looking class.
Exactly. We use letters for the shapes. L0 is an s orbital, L1 is a p orbital, L2 is d, L3 is f.
SPDF. Got it. And the third.
The magnetic quantum number, ML. This can be any integer from minus L through 0 up to plus L. It determines the orbital's orientation in space, how that shape is pointing.
Okay, N for size energy, L for shape, ML for orientation.
Yep. And orbitals with the same n value form an electron shell. Orbitals with the same n and L form a subshell.
Like the N2 shell has a 2 subshell, L0, and a 2p subshell, L1.
Perfect. And the 2p subshell, L1, has 3 p orbitals because ML can be -1, 0, or +1.
Okay, that makes sense. Table 6.2 in the book lays this out nicely.
And crucially, for hydrogen only, all orbitals within the same shell, same n, have the same energy. 2s and 2p are degenerate in hydrogen. 3s, 3p, and third are degenerate. This changes for other atoms, though.
It's incredible how this abstract math underpins so much modern tech. LEDs, lasers, computers, phones.
All reliant on understanding and manipulating electron behavior in materials based on quantum mechanics. It's fundamental.
So let's visualize these orbitals. How do we picture these probability clouds?
We often use contour diagrams showing a surface that encloses, say, 90% of the electron probability.
Okay, what do the s orbitals look like?
They're spherical, like a perfectly round ball centered on the nucleus. As n increases, 1s, 2s, 3s, the sphere just gets bigger.
Simple enough.
If you plot the probability versus distance from the nucleus, you see something interesting. Nodes. Points or surfaces where the probability drops to 0. And n's orbital has n-1 nodes.
Right. What about p orbitals, L1?
These look like dumbbells, or two lobes, on opposite sides of the nucleus, with the nucleus itself being a node, a nodal plane. There are 3 p orbitals in a subshell, px, pi, pz, oriented along the x, y, and z axes. They also get bigger with increasing n.
Okay, dumbbells along the axis. What about d orbitals, L2?
Now it gets more complex. There are 5 d orbitals, starting when n3. 4 of them look like 4-leaf clovers, lying in different planes. Transides, dxc, dxt, dx clovers.
They're leaf clovers. Okay. And the fifth?
The fifth one, dxfel, is weird. It looks like a orbital dumbbell along the z-axis, but with a sort of donut ring around the middle, in the Zexley plane.
Ah, complex shapes?
They are. But the key thing is, within the given subshell, like the 5-third orbitals, they're all degenerate same energy, at least in an isolated atom.
And f orbitals, L3.
Even more complex shapes, 7 of them, starting at n4. Important for heavier elements, but we don't need to memorize their exact shapes right now. Knowing the general shapes of S, P, and D is really helpful later on for understanding bonding, though.
Okay, we've got the orbitals, but we've mostly been talking hydrogen, 1 electron. What happens in many electron atoms?
Now the complications arrive. The big difference is electron-electron repulsion. Electrons repel each other.
And that changes the energy levels.
It does. Specifically, it splits the energy levels of subshells within the same shell. Unlike in hydrogen, for a given n, the subshells are not degenerate anymore.
So 2s and 2p don't have the same energy.
Nope. Energy increases with the ill value. So for given n, ns is lowest, then np, then nf. The 2's orbital is lower in energy than the 2p orbitals in a many electron atom. Orbitals within the same subshell, like the 3 2p's or the 5 3's, are still degenerate, though.
Okay, so the filling order gets more complex. What else do we need?
We need one more quantum number. It came about to explain some fine details in spectra. It's called electron spin.
Electron spin. Like tiny tops.
Sort of. It's an intrinsic quantum property. Alembic and Goodsmith proposed it in 1925. This spin is quantized, leading to the spin magnetic quantum number, EMS.
And it can only have certain values?
Only two, plus 12 or negative 12. We often call them spin up and spin down. A spinning charge creates a magnetic field, which was the key insight.
So 4 quantum numbers now, N, L, ML, and EPS.
Right, and that leads directly to a crucial rule formulated by Wolfgang Pauli in 1925, the Pauli exclusion principle.
Which states?
No two electrons in an atom can have the same set of 4 quantum numbers. It can't have the same address.
What does that mean for orbitals?
It means an orbital defined by N, L, and ML can hold a maximum of 2 electrons. And if it holds 2, they must have opposite spins, 1 plus 12, 1 to 12.
Ah, that's fundamental for building up atoms.
Absolutely. It dictates how electrons fill orbitals and ultimately explains the structure of the entire periodic table.
You know, it's amazing how these quantum properties show up elsewhere, like MRI in hospitals.
Magnetic resonance imaging? Yeah. It actually uses the spin of atomic nuclei, like hydrogen in water molecules in your body, which is analogous to electron spin. It uses magnetic fields and radio waves to map out tissues based on how those nuclear spins behave. Incredible diagnostic tool, no harmful X-rays.
Okay, so we have orbitals, energies, electron spin, Pauli principle. How do we actually arrange the electrons? That's electron configuration, right?
Exactly. It's the distribution of electrons among the available orbitals. And we usually focus on the ground state, the lowest energy, most stable arrangement.
How do we figure that out?
We follow the rules. Fill orbitals starting with the lowest energy first. The Aufbau principle, although the book doesn't stress the name. Remember, each orbital holds max 2 electrons with opposite spins, Pauli.
And we write it down using notation like 1s empty 2s scission for lithium?
Yep. The number is N, the letter is L, S, P, D, F, and the superscript is the number of electrons in that subshell. You can also draw orbital diagrams, boxes for orbitals, arrows for electrons, up or down for spin.
There's one more rule, isn't there? Hund's rule.
Ah, yes. Hund's rule. It applies when you have degenerate orbitals,
Right.
like the 3 2p orbitals or the 5/3 orbitals.
What does it say?
It says that for the lowest energy arrangement, you put electrons into separate orbitals within that subshell first, with parallel spins, all spin up, for example, before you start pairing them up in the same orbital. Electrons prefer their own space if they can have it at the same energy.
Like with carbon, for NCSSU at 2p, the 2 electrons go into different orbitals, both spinning the same way.
Exactly. 2 unpaired electrons.
Writing out the full configuration for heavy atoms must get long.
It does. That's why we use condensed electron configurations. You use the symbol of the preceding noble gas in brackets to represent the core electrons, and then just write the configuration for the electrons beyond that core.
Like sodium element 11. The previous noble gas is neon, 10 electrons, so sodium is just Na3.
Perfect. It highlights the outer shell electrons, the ones primarily involved in chemistry.
And those outer ones are the valence electrons.
Usually, yes. For main group elements, they're the electrons in the outermost shell, highest N. This is why elements in the same group, like lithium, He2s, and sodium, Na3s, behave similarly. They have the same number of valence electrons in similar orbitals.
What about transition metals, the D block?
There, the N1d orbitals start filling after the N-Taus orbital. So for manganese element 25, it's R4 sum 3Da. The third electrons fill according to Hund's rule. Defining valence electrons gets a bit more nuanced there, often including the d electrons.
And the lanthanides and actinides, the F block elements below.
They involve filling the 4f and 5n orbitals, respectively, often quite similar chemically because the differences are deep inside the subshells. We should also mention there are a few exceptions, anomalous configurations like chromium or copper, where an electron jumps from an s orbital to a d orbital to achieve a half-celled or fully filled d subshell, which offers a bit of extra stability. But there are exceptions, not the main rule.
So putting this all together, the periodic table isn't just a random arrangement.
Not at all. It's a direct consequence, a map of electron configurations. It's probably the most powerful predictive tool in chemistry.
How so?
Elements in the same column, group, have similar valence electron configurations. That's why they have similar chemical properties. Group 1 are all Ns, Group 2 are Ns-Sol, halogens are Ns-P, noble gases are Ns-P except helium.
And the rows, the periods.
The length of each period, 2, 8, 1832, reflects the number of electrons needed to fill the available shells and subshells according to the rules. 2 electrons for N11s, A for NLs2, 2s 2p, etc.
The table has distinct regions too, right? The blocks?
Yes, the S block, groups 1 to 2, P block, groups 13, 18, D block, transition metals, groups 3, 12, and F block, lanthanidus, actinides. The block tells you which type of orbital is being filled for the outermost electrons.
So you can just look at an element's position and work out its configuration.
Pretty much. Let's take selenium Psi element 94. It's in period 4, group 16, a P block element. The previous noble gas is argon R. Then you cross the S block in period 4, 4 sexes, then the D block, which is N1, so 3D arrays. Then you enter the P block in period 4, and selenium is the 4th element in 4PO.
So RTP at 4 sections, 3D equals 4PO. That's neat.
It really is. And for these main group elements, S and P blocks, the valence electrons are just the ones in the outermost shell, highest N. So for selenium, the valence electrons are the 4 sextants and 4PO electrons, 6 in total. We don't count the filled 3D Euclides as valence for representative elements.
The periodic table really is the ultimate cheat sheet for this stuff.
It absolutely is. Structure dictates function, and electron configuration dictates chemical properties, all laid out for you.
Wow. We've gone from light behaving strangely through Planck and Einstein's quantum ideas, Bohr's early model, de Broglie's matter waves, Heisenberg's uncertainty, all the way to Schrödinger's equation and the quantum mechanical picture of orbitals and electron configurations.
It's quite a journey. And the key takeaway is that this isn't just abstract theory. Understanding electronic structure is the foundation for understanding why elements react the way they do, where molecules form, why materials have the properties they have. It's the basis of chemistry.
So here's a final thought. This bizarre quantum world, ruled by probabilities, fuzzy electron clouds, quantized energy. This invisible realm is what actually creates everything tangible, all the diversity and properties of the materials you see and touch every single day.
It's a pretty profound connection between the incredibly small and the world we experience.
We really hope you enjoyed this deep dive into the electronic structure of atoms. Keep asking questions, keep exploring.
Thanks for joining us. We'll catch you on the next deep dive.